Okay, so this is a rather tricky problem, and we're going to a physics problem, and we're going to try and solve it without like referring back to a textbook or using normal like equations of motion. Okay, we're going to try to solve this using some graphs, using some algebra, geometry, and of course calculus. Okay, so this problem that we have here is as you can see, there is there's an airplane, and the airplane's carrying a rocket. And what's going to happen is the airplane's at 12,000 or 12 kilometers or 12,000 meters, and it's flying, at 850 kilometers per hour. So it's flying straight at 850 kilometers per hour. So that's obviously its velocity. All right, so what's going to happen is it's going to drop the rocket. The rocket's going to drop, and it's going to be in free fall. And then after t seconds, capital T seconds, what's going to happen is the rocket engine is going to start to light, or the motor on the rocket is going to come on, and instead of the rocket being in free fall, it's going to start accelerating up. So, and it's going to go up like this. Okay, and when the rocket engine starts going, the combined acceleration, meaning both gravity and the rocket together, is going to be 3g. So it's 3g, 3g's, right? And obviously g is the acceleration due to gravity, or 9.8 meters per second squared. Okay, so and it's also at an angle of 30 degrees with the horizontal. Okay, so it's not 3g straight up; it's 3g's, like I said, 30 degrees up from the horizontal. So the problem is that the rocket drops down, the engine comes on, it lights, and it obviously it's going to go up, right? Well, what I want to know is I want, as the rocket is approaching the same height as the airplane, so the same y height. So the airplane's at 12 kilometers or 12,000 meters up. When the rocket also gets up to that same height, that same altitude, 12 kilometers, it also needs to be 1,000 meters away from the airplane. So the airplane needs to be behind it 1,000 meters away while it's going up. So as it's coming up here, it needs to be 1,000 meters in front of the airplane. And they just do that for safety reasons, because you don't want the rocket coming up and maybe hitting the airplane or getting in its wash or whatever. So for safety reasons, as the rocket is coming up at the same altitude as the airplane, you need like 1,000 meters or 1 kilometer like spacing distance for safety. And so the question is, what is T? What is capital T? Meaning, when you drop the rocket from the airplane, how long should it drop, i.e. how long should it be in free fall until you turn on the engine? Okay, but it has to satisfy the constraints, as when it comes up over the altitude, when it comes up to 12,000 meters, it also has to be 1,000 meters in front of the airplane. Okay, so it has to obviously be within those constraints. Okay, so we're going to do a couple things. One is we're going to set our origin. You know, obviously you can set your origin to anything. So I'm going to set my origin to this. So this is going to be like 0, 0. Okay, this is going to be 0, 0. It is essentially the 0, 0 is the airplane right as it drops the rocket. Okay, so we're at 12,000 meters. So we're just going to like skip that. We're just going to, we don't really care about it being 12,000 meters up. We're just going to say our origin is just 0, 0, and then we'll just have like negative. We'll have a negative position, okay, which is fine. Okay, so number one, our origin 0, 0 is at the airplane. as it drops the rocket. Number 2, the airplane is not accelerating. It's just going at a constant 850 kilometers per hour. And what we're going to do is we're just going to convert this into a standard meters per second velocity. And if you do that, you'll end up with 236.11 meters per second. Okay, so we're just going to convert that. The next thing we want to do is the combined acceleration of the rocket once it turns on it's at 30 degrees to the horizontal, so this is 30 degrees. And it's at 3 Gs. So it's at 3 Gs. Okay, so what's 3G? So 3G is equal to 3 times 9.8, which is equal to 29.4 meters per second squared. So that's the acceleration, the combined acceleration, gravity plus the rocket. Okay, so this thing right here is actually, well, it is 3G, of course, but we're going to make it 29.4. Okay, so what I want to do is I want to figure out this side. I want to figure out the acceleration in X, in the horizontal direction, and I want to figure it out in the vertical direction as well too. Okay, so if you say 29.4 times, now I want to go to the bottom, so that's adjacent to the 30, so I would say cosine 30 equals something, and then over here the vertical is 20. Hold on, let me turn this off. Yeah, it'll this is like this new iPad software where it'll try to answer for you. I don't want that to happen, so I just turned it off. Okay, and then the vertical, I want it to be 29.4 times the sine of 30. Okay, and the cosine one is 25.46 meters per second squared. This is acceleration in the horizontal. And the other one is 14.7. This is 14.7. Obviously, it's meters per second squared. Okay, so the origin is at the airplane. It's traveling at a constant velocity of 236.11 meters per second. And the rocket, once it turns on, is going to have a horizontal component of 25.46 meters per second squared and a vertical component of 14.7 meters per second squared. Okay, so what I want to do now is, and this is how I like to approach these problems, is because this is a dynamics problem, right? I like to solve these using graphs and sort of like use your own intuition, because you could pull out a textbook and go, okay, on page 3 there's this formula, and on page 10 there's this formula, and let's combine the formulas, which is fine, which is great. I have nothing against that. I'm just showing you like a different way, a more, I don't know, I guess intuitive way to solve this problem, or at least I like it. All right, so. All right. Let's put a line here. All right, so what I want to do is I want to create some graphs. I want to create the velocity of the airplane in X and the velocity, and then let's do that. And then over here, I'm going to do its position. So the position of the airplane in X, and then we'll also do Y too. We'll put it on one page. So the velocity of the airplane in Y, and its position of the airplane in Y. Okay, so its velocity. So up here at the top, its velocity. So let's draw let me go ahead and do this. Okay, let's go ahead and draw my axes like that. Okay, and so obviously the velocity, when it says velocity, obviously that's in meters per second, and then that's relative to time. It's a function of time, and then your position, obviously that's in meters, and that's a function of time as well too, right? So time is always on the x-axis, right? Little t for time. Okay, the velocity of the airplane. So in x, so this is our x. Remember, you want to take your different motions, velocity, acceleration, position, and you want to separate those into the different components. Your x component, your y, your y component, and your z. So the x is horizontal, right? So what is his initial x? His velocity in x initially? Well, it's 850 meters kilometers per hour, or 236.11, and that's it. Of course, that this is in meters per second because it's velocity, right? So that's his initial x velocity. Now, is it changing? No, it's not. The airplane is going at a constant speed, constant acceleration. So because it's constant acceleration, you're just going to draw a flat line, right? Because this line right here represents acceleration, and so because the acceleration is constant, then it's flat, right? There's no slope on it. So the equation of this line is just 236.11. That's the equation of that line. Okay, now let's talk about the velocity in y. So down here, the velocity of the air. So this airplane, y of course means up and down. Is the airplane moving up or down? No, the airplane is just going straight. So his initial velocity in y is 0, and the line looks like that as well too. It's 0, so it's just 0. Because he doesn't have a y. Great. Now let's look at our position in x. Okay, our position. So you want to do your velocity first, and then what we can do is we can integrate that to find our position, right? In order to go from here to here, you just integrate. In order to go from here to here, you just integrate. Okay. All right, so that looks pretty good. All right, so our position in x. So you need your initial position first, right? So where is the plane at initially relative to our origin? Remember our origin, 0, 0, where was that at? That was right where the airplane is. So his actual initial position is in x, it's at the origin. It's 0. Okay. Now, what does that function look like? What does his position look like? Well, all you have to do is take this and integrate it, the 236.11, and just integrate it, and that becomes his position. Okay, great. And so, well, 236.11 is just 236.11 t, right? So then that becomes this. So you integrate 236.11 on the velocity in the air in the x, and then you get you get the function, the position function. So this is just 236.11 t. Okay. And so yeah, so if you're wondering where is the airplane at in x after 5 seconds, you would just say 5, that's your t, times 236.11, and that will tell you where the airplane is relative to the origin that was placed down. So wherever that origin that was placed, that's how far you are away from that origin. Okay. And then now let's talk about the position of the airplane in y. Well, he doesn't have so the velocity in y isn't changing, and our initial position was 0. Remember, because the airplane is at 12 kilometers, but we actually set our origin, because you can set your origin wherever you want. I set it at the airplane. I set it at 12 kilometers. So his origin is actually 0 based on where I put the origin. And what about the function? Well, because the velocity of the air in y is 0, so therefore when you integrate that, you're also going to get 0. You're going to get that. So this function is just 0, right? And that makes sense because the airplane is not moving in y. The origin was set for 0 in y, and he's not moving. So that means it means the position, the velocity, and the acceleration are all 0 in y. So we don't need to worry about that. The only thing we need to worry about is just x. Okay, so that's great. So this is our airplane. So these are the 4 functions for how the airplane is moving in both x and y, which is great. Now what we need to do is we need to figure out how the rocket is moving in x and y. Okay, how the rocket is moving. So let's bring this down. Okay, maybe I'll change this to black. Okay. I think I'm going to make these a little bit bigger because the rocket actually gets a little bit trickier. Okay. All right, so I'm just consulting my notes here. I think I'm going to do this one first. So I'm going to do x first, and then I'm going to do y. Yeah, so I have notes with this one because this one, like I said, is actually a little bit tricky. Okay, so let's talk about the velocity. So this is the rocket. So this is the velocity of the rocket in x. And let's also, down here at the bottom, we'll do the position of the rocket in x. Okay. Something like that. Okay. So what I want to do is let's create, I'm going to do this here. Maybe this here. And so obviously the velocity in x is in meters per second. All right, this is in meters per second. This is just and the position, of course, is in meters. Okay, the rocket. Where is he at? So what I need here is just like in the airplane, what is his initial velocity? We take the initial velocity, and then we figure out the function that moves him through space. But we need to find out where he's at first, right? So the velocity in x, well, the rocket is actually attached to the airplane, right? The airplane is moving at 236.11 meters per second. So if the rocket is attached to the airplane, that means the rocket is also moving, right? At the same speed, because he's attached to the airplane's pulling him along at the same speed. So whatever the airplane's moving at, the rocket's moving at as well too. So we'll put a little point here, right here, and this is positive. So this is the 0 line, and this is 236.11. That's right there. That's that point. That's his initial velocity. Okay. Now. Now, is that velocity actually changing? No, it doesn't change. Well, it can't. I mean, the velocity will change, but it will change due to external events. Okay, so what will actually change his x velocity? So when it drops. Does the x, remember x means back and forth or horizontal. Does gravity, so when it drops, remember the airplane is carrying the rocket, and the rocket drops. And then the rocket drops for t seconds, and then the engine comes on. Okay. So let's write in here t seconds, okay? And maybe we'll do the same down here as well too. T. So between 0 seconds and t seconds, that means the rocket is in free fall. So he's falling down. So if he's falling down, straight down, then does his x velocity change? No. Gravity only changes y, right? Gravity only changes y. So his x velocity is actually still the same. So what we can do is maybe I'll just change it to this, and we can do like this. Okay? So the velocity is not changing due to gravity. Okay? So we'll just leave that as a nice horizontal line, and this function, of course, is 236.11. Okay? Because gravity's not altering it. Now, what we can do is we can say, okay, but what happens after time t? Well, after time t, the rocket engine comes on. And when it comes on, it's going to provide 25.46 meters per second squared of acceleration. And so what you would want, though, is you would want to say something like, okay, at time t, what I would like to see is a line that looks like this, going 25.46 t. Okay, that's what I would like, because at time t, that acceleration begins. Okay, but then how can you do that? So this function that I just wrote right here is actually here. It's actually here, right? 25. If you were to plot 25.46 t, that function, it would actually go through 0, right? That's its y-intercept is 0. But I don't want to be there, because this acceleration actually starts at capital T, time equals capital T. So what I would like to do is I would like to take this function that is over here, that is actually over on the left, and I want to move it. I want to move this function this way. I want to move it to the right. Okay, I want to move it to the right. So how can you do that? Well, if you remember your algebra, you just take its t, 25.46 t, minus capital T. So what that'll do is that'll just move that function to the right by whatever that is. And the capital T it's like a constant, right? It's like 7 or 9 or whatever, okay? If it was little t plus big T, it would shift it to the left, and if you're doing subtraction, it shifts it to the right. Okay, so we really have two functions here. We have the initial velocity in x, and we'll just leave that one alone, right? He's chilling along at 236.11 meters per second. That's his initial x, and nothing's changing that up until time t. And time t, something different happens. The engine comes on, right? The engine comes on, and when the engine comes on, it's going to provide 25.46, like I said, meters per second squared, and that's what this function looks like. And because it was normally at 0, but we're going to move it over, right? We're going to move it over t, capital T spaces. And we do that by just saying little t minus big T. Great. And so what happens is basically you have two functions, right? You have the horizontal function and the diagonal function. What's going to happen is you actually just add those together, and that creates the composite function, which is how it's really moving, right? So if you were to add these two functions together, you're like, well, how would I do that? Well, you would say, maybe I'll change my colors here. You would say 25.46 little t minus big T plus 236.11. And so that's the velocity in x with respect to time. So you could say, if you wanted to, the velocity in x with respect to time, or as a function of time, is equal to 25.46 parentheses, little t minus big T, whereas big T is like a constant, and plus 236.11. So this blue one is the combined of this function and this function. So they both combine together, and this is like the composite function. Now I'm not drawing the actual composite function, but you could of course easily graph that out if you wanted to. So that's what it looks like. That's what the velocity looks like in x. Okay, so but what does the position look like? Okay. So remember, in order to go from velocity to position, you have to integrate. So we're going to go from here to here, right? We're going to have to integrate that function. Okay. Now, before we do that, what I would like to do is I would like to figure out what my initial rocket position, the initial rocket. So the rocket, where is his initial x at? Well, it's at 0. It's the same as the airplane. Remember, because the rocket is attached to the airplane, right? So because the airplane right here is at 0, well, then the rocket is also at 0. That's his initial position. So we'll just like put that right there at 0. And obviously that's 0. This is the 0 line. Great. So, all right. So what do I want to do? Well, what you could do, if you wanted to, is you could take those two functions that I had up here at the top in velocity, and you could just integrate both of those individually, and maybe we'll just do that, okay? Obviously, you could integrate the whole thing at the bottom, but integrating the whole thing, the integrating the composite function is the same thing as integrating the individual functions. Okay, the individual functions. Okay, so let's just take the 236 in the velocity at the top, the 236.11. Okay, the one that's horizontal. Let's just integrate just that one. Okay. So if I do that, you'll end up with this. 236.11 t. Okay, so if you integrate just that function, 236.11, you end up with 236.11 t. Great. Now, what about this other function, 25.46 t minus t? Well, what does that look like? Well, what would normally, I'm just going to show this over here. I'll end up erasing it. What normally happens is if it was just like 25.46 t, well, you would take half of that, which is like 12.73, and so it would be like 12.73 t squared, right? But it would be a parabola, so it would look something like this. It looks something like this, okay? But what I want to do is I want to actually shift it over. I want to shift it over 5 so it looks like that instead. So I'm going to take that parabola and I'm going to shift it over. All right. But the information is already there. If you look at the top at the velocity, it's 25.46 t minus t. All you have to do is just integrate that, right? And if you do, you'll end up with, and I'll do that. Maybe I'll draw this little like dotted line or something like t. Okay, and what it'll do is it will create this thing, this function, which is, well, you have to take 25.46, and because it's already sloped, it's already a function of t. When you integrate it, it becomes t squared, right? So it becomes, and then you have to take half of it. So 25.46, you have to take half of that, and so that ends up at 12.73, because that's half of 25.46, and then the t minus t, then that just becomes t minus t squared. Little t minus big T squared. Okay. And so there you go. So that's the composite. Sorry, that's not the composite. Those are the individual functions. You have 26, 200. So the position of the rocket in x is actually, I integrated two functions from velocity, And one was 236.11 t, and the other one was 12.73 times little t minus big T squared. Just like on the top, you can just add those together, right? So I can say 12.73 little t minus big T squared plus 236.11 little t. And this function is the position in x of the rocket as a function of time, little t as a function of time. Great. And so that's actually what I want. At the end of the day, I'm looking for the position. I'm looking for the position functions, the position in x and the position in y. And I need that for both the airplane and the rocket. So I actually have the airplane. Remember that? The airplane was up here. What does his position in x look like? It's 236.11 t, right? So the airplane one, let's change colors here. The airplane in x, his position, let's say p, was, let's just look again, 236.11 t. 236.11 t. And what is the position of the rocket? We'll say ROC for rocket in x. What does he look like? Well, I just did that. That's 12.73 little t minus big T squared plus 236.11 t. Don't forget that t. Great. And so what I can do is I can just set those equal to each other, right? So, because what you want to know is when is the x of one equal to the x of the other? But there's a slight wrinkle in that I want to take the the position of the airplane, which is that function, 236.11 t, and I want to add on 1,000 meters, because I don't want to find out where these two functions interact by themselves. I want to know where the position of the rocket is 1,000 meters in front of the airplane, right? So let me just draw this just to show you. So let's imagine that the airplane is here. Let's imagine the airplane is here. And let's imagine the rocket's coming up, right? The rocket's coming up, and the rocket's right here. So let's imagine it's at the same height, it's at the same altitude. But so the airplane is here, right? Obviously it has some x position. Let's imagine the x position is like 5. So his position in x is 5, just some random number, okay? Well, I want the rocket to be 1,000 meters in front of him. So if that's true, then I need this to be 1,005. Well, then how did you do that? Well, you take the airplane, plus 1,000. So I want the airplane's x plus an additional 1,000, and that should equal where the rocket is in x. Okay. So that's what we're going to do. We're going to say 236.11 t plus an additional 1,000, so that's for the airplane. Where does it equal? 12.73. This is the rocket. 12.73 little t minus big T squared plus 236.11 t. And so there we go. We have a function. Yes, I'm just checking my notes to make sure this is correct. Okay, so what's happening here is you can notice that you can actually just subtract 236.11 t here and here, and you can just simplify this function down to 1,000 equals 12.73 little t minus big T squared. Okay. Let's do like this. So there we go. That's our one main function. Basically, we're going to have two functions. We're going to have a function for the x and a function and another function for y. And we'll have two functions and two unknowns. The two unknowns are little t and big T. So in order to solve a system of equations, obviously if you have two unknowns, you have to have two functions. If you have five unknowns, you have to have five functions. Okay? So this is our first function, which is great. And now what we have to do is find the second function in y. Now we already have the rockets, we already have the airplane's y, because the airplane's not moving in y, right? The airplane's only moving in x. So the airplane one is done. So now let's do the rocket's y. Okay, this one is out of all of them, this one is the most tricky. Okay, so let's put a line here. And now we're going to do okay, just checking. Now we're going to do the velocity of the rocket in y, and then this is the position of the rocket in y. Okay, all right. So let's do that. Let's put this here. Obviously, this is this middle is the 0 point. Okay, my graph. All right. So the rocket in y. Let's think about this one for a second. Or the velocity. So remember the top is the velocity. So what is his velocity initially? So right as the airplane, remember the airplane's holding onto the rocket, it drops it. Right before it drops it, what is his y velocity? Remember, y is up and down. What is it? Nothing. It's 0. Because it's still holding onto the airplane. The airplane is not moving up or down. He's still attached to it. Okay. Now, and then I'm going to draw a time. We'll call this a time t. Time t, because time t is where something changes, right? Okay, so I have the initial velocity 0 in y, and it's going to drop. And so once the airplane releases it, the bolts, and the rocket's going to what? It's going to free fall at what? Here, it's going to go down like this at negative 9.8 t, right? 9.8 meters per second squared. And so it's negative 9.82. That's the slope. Remember, the slope of this line represents acceleration. And so that's negative 9.8 t. So it's negative because it's going, because his velocity is increasing negatively the more that time passes, right? In 1 second, it's almost negative 10 meters per second. In 2 seconds, it's like almost 2 times 10. That's like negative 20 meters per second, etc. Okay? So this guy, he's in free fall, right? He's in free fall. Okay, maybe I'll continue like that. But then at time t, something happens. At time t, the rocket engine comes on. So the rocket engine is 14.7. So what you could do here is you could say like this, and this is 14.7. Okay, t. Now, normally this line, just like the one I just showed you before, would be right here. Right, it would be right here, but I'm going to move it over. And so in order to move it over, I'm going to move it over t spot. So I'm going to go little t minus big T. Okay, so that's that function. Now here's the tricky part about this. Now you might just think, okay, well I'm just going to go ahead and this is fine. I have two functions, negative 9.8 t and plus 14.7 t minus t. I'll just put them together. Well, the problem is that the 14.7 is combined. That's the combined acceleration of gravity and the rocket. So that means effectively that the gravity from this one's perspective at time t, it shut off. You can kind of think of it like that. And if it's shut off, that means it's effectively zero. It's effectively zero. Okay. There is no gravity. Well, like I said, there is gravity. It's just the gravity plus the rocket motor is combined into the 14.7. It's combined into the 14.7. So you're like, okay, well, how would I? Basically, what I want to do is I want to figure out how to make this line straight. This blue dotted line. Well, the gravity is going from 0 to the blue line. That's negative 9.8 t. But after that, I want it to be straight. Okay, I want it to be straight after that. Well, how am I going to do that? Well, all you'd have to do is just invert. You could just add another function, right? If you added plus 9.8 t right here, let me just do this one here, plus 9.8 t, okay. And so what'll happen is at time t, capital T and beyond, the negative 9.8 and the positive 9.8, those guys will interact. They're opposites, so they'll just cancel each other out, right? They'll cancel each other out, and so the net acceleration is just 0, right? Because one's pulling down, negative 9.8, one's pulling up, positive 9.8, and so the net effect is 0. So you're effectively zeroing out this line. Now, you might be thinking to yourself, well, if that's but if you add this also it's 9.8 t, it's t, little t minus big T, right? Because you have to shift it over. You have to shift it over. Now, what you could do is you could just add 9.8 and 14.7, right? You already have 14.7, right? And you could just say, all right, well, I'm just going to add an additional 9.8. That's basically 10, right? And then 14.7 is roughly 15, so 15 and 10. So you could say, well, I'm just going to do 25. I'll just do 25 meters per second squared, which is fine. You could do that. Or you could just do 14.7 plus 9.8. Obviously, those are the same things, right? So you could either have 2 or you could just have 1. Either way. Now, the question you might be wondering is but if you add these functions together, isn't it going to mess this area up here? So, like over here, like this area in here, is it going to mess it up? Because you actually have other functions. You still have this guy, right? He doesn't stop there. He actually goes through here. So you have, and this other one's red. Let me just continue with the red one. Isn't that gonna mess this area up over here? Yes, it would, but you actually don't care about that. The only part I care about, the only part on this graph I care about, is between capital T and little t, where little t is where where the rocket and the airplane meet. Right, so remember, I'll end up erasing this. So the airplane, right? The airplane's going like this, and the rocket's going like this, right? And then the rocket comes up, and the rocket's right here, and the airplane's right here. Remember that it needs to be 1,000 meters difference between this. Needs to be 1,000 meters, right? That's 100. 1,000 meters difference. But what is this time? What is this time right here? What time is this? When it both goes up, it's at the same altitude as the airplane, but it's 1,000 meters in front. What time is that? That's little t. Okay, that's what I'm looking for. That's what little t is. Or when I find it out, that's what it is. Okay, and so that's going to be somewhere over here. Let me just change this. That's going to be somewhere like over here somewhere, all right? Like, I don't know where it is. Hold on, let me just take this back. So T. It's going to be, let's say it's here somewhere, right? So as long as this graph is good between here and here, then it's fine, okay? So you're like, yeah, but the numbers below the big T are not actually going to be correct because of all those functions interacting. That's true. The only part you actually care about is where do these functions touch each other? Where do they intersect? Between, as long as it's good, between the big T and then this dot over here, As long as that's good, then you're fine. And the big T, if you look at it, the 14.7, right? The 14.7 and the 9.8, where are they actually at? So here, if you look at this thing, they're actually right here, which is 0, right? They're actually at 0. So if you were to add them up, that's 0 plus 0, because they're actually at 0 there. And then here, this guy here is at what? Negative 9.8 times, in this case here, times big T. Okay, whatever T is. So this point actually is correct, because the 14.7 and the 9.8, the positive 9.8, actually are at 0 there. So basically you're just saying 0 plus a negative 9.8 times big T. And then after that, in the yellow region, the 14.7 is good, but then the positive 9.8 and the negative 9.8, those just cancel each other out. So those end up just being 0. Okay. So like I said, as long as the graph is good between capital T and little t, then you're fine. Outside of that, you don't care. Okay, so outside of that, you don't care. So as long as the functions are correct between those points, then that's all that matters. Okay, great. Okay, so now of course we're gonna have to like take this stuff and we're gonna have to integrate it, right? So you're gonna take this and you're going to integrate in order to do these things. Now, I really have, how many functions do I actually have up here? Well, I have the negative 9.8 t, and then I have the positive 9.8 t minus t, and then I have the 14.7, right? So I have kind of three. I kind of have three functions. Once again, you could add 9.8 to 14.7 roughly make it basically 25. That's cool. You could do that. It's obviously it's like the same thing. Okay. So let's do this one. So let's do the negative 9.8t. So first of all, the position in y. Where is a rocket's position in y initially at? Well, it's a 0, right? Because he's attached to the airplane. And then as it drops, once it drops, obviously it's going to go like that. It's going to go down like that. Okay? At t. Okay? And so that function is the negative 9.8t, but you integrate it, right? So then this becomes negative 4.9 because you just take half of 9.8, and then you take t and make it t squared. T squared. Okay? So that's that function. And then the other function is just the 14.7. You just take half of that, which is 7.35, and then you have to flip it over, right? So it becomes something like this, right? So you take 14.7, you take half of it, and that's 7.35. Little t minus big T squared, okay? And it's t minus t because initially, right, it would be like here, and you're moving it over. You're going to move that function over. Okay, so I have that, and then obviously I also have the same. You also have the same parabola if you want. Something like this, which is the 9.8. Oh, sorry, it would be half. It would be half of 9.8. It would be 4.9. So 4.9 t minus t squared. Okay. And so what that'll do effectively is that'll cause this to go away. Okay, it'll cause that to go away. It'll just be 0. It'll be no net acceleration. Okay. Due to that. Great. So now we have three functions, right? So and then they're equal to 0. Okay. So so let's put all of our functions here together. So I have negative 4.9 t squared. That's that one. Plus 4.9 little t minus big T squared. And so remember, that just cancels out the other one after T, after big T. Okay, it cancels it out. And then I have the upward acceleration of the rocket, which is 7.35 T minus T squared. And what do I want to know about this function? Well, this is this position in y, and what I want to know is where does it go up? Because remember, the rocket is falling down, 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 so it's going negative. Remember, our origin is at 0. So let me just draw this again. So here's the airplane, right, and then here's the rocket. Sorry, rocket, and then here's 0. Here's a 0 line. So the rocket is falling, 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 falling. What's its position? It's negative, 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 less negative, less negative, less negative, less negative, less negative. Boom, right here, it's 0. So what I want to know is where does this and this function, this right here, is the position of the airplane in y. That's that function, and I want to know where does this function equal this function. Where do these two functions interact? Where do they collide? And they collide right here. And that's at time little t. That's at time little t. So I want to know where does this thing equal 0. Okay? So then that's basically it. So once you have that's your y. And you can see I have little t and big T here. And then I have this one, also that green one. Right? I have this function right here. And then I have this function. So I have two functions, and inside the end, and I also have two unknowns, little t and big T. And so once you do that, once you set that up, then you can obviously plug that into any software that can solve a system of equations. And then once you do that, you will end up with T, capital T, equal to 5.15 seconds. So what that means is so in conclusion, if the airplane drops the rocket, let the rocket drop for 5.15 seconds. After 5.15 seconds, light the engines on the rocket. The rocket will then start accelerating upwards, and it will be at the same altitude as the airplane, but it will be 1,000 meters in front of it. And so that's it. Cool. Once again, you notice we just spent a lot of time doing this whole problem, and I didn't pull out any equations, any equations of motion. I didn't consult a textbook or anything like that. We just basically looked at the problem, broke it down into its individual components: acceleration, velocity, position, and we used some geometry and algebra, and of course calculus, both differentiation and integration, and some common sense, to try and solve this problem. The tricky problem here is when you're doing these things, especially when multiple things are happening, like, oh, the rocket's fall is in free fall. Okay, now the engine's on. Now the engine's off. It's like, what's happening there? You basically have different functions are happening, right? And you kind of have to sum those different functions together to create an overall or a composite function. So when you're dealing with something that's like changing, like, oh, this is on, it's off, and this is happening, and this is happening, those are different functions, right? And you're going to have to like combine those together to create an overall or a composite function. So that was really the main thrust behind this problem. All right, that's it.